My name's Daryl Faulkner. I've been an architect with Mix for quite a while now, and I'm going to be talking about Z13 multi-threading and something you can do in ZOS 2.1, even if you're not doing multi-threading, that will break Mix. And it's called ProcView Core. We'll talk about that later. So IBM, back in the late 80s, they were using a chip technology called bipolar. And it became a dead end for them as they got to faster and faster cycle speeds. The chips just got too hot. And I don't know if you're as old as me, you remember these thermo-controlled modules and chilling systems they had to have to keep the CPCs cool enough that they wouldn't melt. And IBM abandoned that and went to a CMOS technology back in the early 90s, and they were very slow at first. It was a big jump backwards, but they've continued to evolve and evolve and evolve and get faster and faster, and now they're much faster than those old bipolar chips. But once again, IBM has hit a technology roadblock. And if you look at the top chart of numbers, that's showing the 5 most recent CPCs that IBM has given us: the Z9, Z10, Z196, the EC12, and now the Z13. And you can see the number in the white area is the cycles per second, and it's expressed in gigahertz, billions of cycles per second. And you can see the Z9 was just under 2 billion cycles per second. Big jump to the Z10 up to 4.4, then 5.2 with the Z196. The EC12 got up to 5.5 billion cycles per second. And now if you look at the Z13, it went down. And there's a very good reason they did that. And if you look at the second chart, each one of these cycles per second is how fast the clock is running on the individual chips that you buy when you purchase one of these. You know, the CP engines, the ZIP engines, ZAPs, IFLs. This is what the clock speed is. And the computer operates digitally. It can do things every time a cycle clicks. So with a ZEC12, there's 5.5 billion times a second the machine can do stuff. But each one of these chips also has something called a level 1 instruction cache and a level 1 data cache that's attached right to the chip. And when your program is running, or your TSO session, when you're dispatched and you're actually making use of that chip, programs need the next instruction, and they need the next piece of data. And they always get that information from the level 1 cache. If it's not in the level 1 cache, it needs to be obtained from elsewhere in the cache hierarchy or real memory. But it needs to get placed in the level 1 cache, and then the instruction or data can be made use of. And you can see with the Z9, the size of the level 1 instruction cache was 256 kilobytes. And the size of the Z9 data cache was 128 kilobytes. And that's pretty small. I mean, when you think that memory on these new CPCs can be terabyte size and so on, the reason they're so tiny is that IBM has a design feature on their CPCs so that when the instruction pipeline needs the next instruction or the next piece of data, it looks in the level 1 cache. The design objective is if it's in the cache, it can find it and retrieve it in one machine cycle. So when there were 1.7 billion machine cycles per second on the Z9, and the chip technology and memory technology they had at that time for the level 1 cache, they had to limit the size of these caches to 256 and 128 bytes to meet that design objective. And it's kind of like if you have a small room as a human and you go in there and there's only 10 people in there and you need to find one of them, a piece of data or instruction, you can find it at a glance if there's only 10 people in the room. But if there's 1,000 people in the room, it's going to take a lot longer to find the person you're looking for. And that's basically, it's a simple analogy, but that's why these caches have to be so small. And as the cycle speed increases, you look at the Z10, there's a big jump in cycle speed, more than double. You can see that the cache sizes drop dramatically, 256 down to 64. And the reason was there's less time at that speed per cycle to find what they're looking for in the caches. And you can see with the down arrows, they were able to keep the cache size the same size with the Z196, maybe improved chip technology. With the ZEC12, they had to shrink the data cache a little more from 128 to the 196. But they've reached a limit. If they take the ZEC12 up to 7, or the next box up to 7 or 8 gigahertz, the caches are so tiny that not much data or instructions can fit in them. And what that means is that the likelihood of the program finding what it needs in the level 1 cache is lower because you just can't put that much stuff in there. So what they did with the Z13, they actually slowed it down a little bit. They went down to 4.8 gigahertz, and they increased the sizes of the level 1 instruction and data caches. And they did that to accommodate something called multi-threading. And with multi-threading, IBM has branched out. They've sort of reached the limits of technology so far as increasing gigahertz to get more capacity. So they've slowed it down a little bit, made the caches a little bit bigger, but they're going to allow these processing chips, these initially ZIPs for ZOS, run 2 workloads simultaneously within the same chip. And that means that 2 workloads are going to be sharing the same level 1 cache. And there's very smart scientists working at IBM, and they've figured out that this seems to be the optimum cycle rate and cache size to be able to accommodate 2 workloads sharing the same level 1 caches. So that's kind of why it's happened in a nutshell, why this multi-threading has happened. And just the bullets real quick. When it finds what it needs in the level 1 cache, the machine is humming, boom, boom, boom. But when there's a miss, on average, it takes hundreds of cycles, hundreds of those cycles to find, this is on average, to find the item that it needs, the next instruction or data. So you're clicking, every cycle you're getting work done, you have a miss. Your workload is basically frozen. From a performance perspective, it looks like you're still running, but the machine is actually searching for the data or instruction, and the workload is just a zombie. It's not getting anything done. So with SMT, IBM has come up with a way to try and make these cores productive while a cache miss is being resolved. So if you have 2 workloads running on the same core, if one of them experiences a level 1 cache miss and the rest of the caches in memory are being searched for what's needed, the second workload can continue running if its stuff is in the level 1 cache. And they obviously ran millions of scenarios and found out that this is a good way to increase productivity from the cores that you buy for your CPC. Now, running 2 workloads on 1 core is not as productive as having 2 cores. So if you buy 2 CP engines, you're going to get more work done than you, if multi-threading worked on CP engines. If you bought 2 CP engines, you would get more work done than if you just had 1 CP engine. But it is more productive than having one workload running on one engine during these times of cache misses where basically nothing is getting accomplished. No productive work is being accomplished. So just real quick, we all need to adopt a new terminology. We have to start calling these things cores. In the past, I've called them engines. In mix, we call them processors all over the place, number of CP processors, number of zip processors, number of IFLs, and so on. We have to start calling these cores. And cores are the things that you buy. When you buy a Z13 or a ZEC12, you configure it with 12 CP engines and 6 zip engines and 4 IFL engines and so on. And when you define your LPARs, you assign so many logical cores to those LPARs. Here I have an LPAR called SYS1 with 3 CP cores and 2 zip cores, and an LPAR called SYS2 with 2 CP engines and 2 zip cores. So there's a big change in terminology. Processor, we can't call these things processors anymore. We must call them cores. And Prism is the thing that manages all of your LPARs, not just COS LPARs, but VM LPARs, IFL, or coupling facility LPARs, VSE power LPARs. Those logical cores that you've assigned to each of those LPARs are dispatched to the physical cores in your KEK based on the weights that you've assigned for each LPAR's cores. So you can make certain LPARs more important than other LPARs from a Prism dispatching perspective, who gets the most time on the real cores by adjusting the weights of your various LPARs.